Okay, so I have this element in plane stress here with a shear stress of 40 megapascals, negative 10 megapascals in the y, 50 megapascals in the x. And so I want to find a couple things about it. I want to find out where the principal strains are located. I want to know where the what the principal stresses are. I want to know what the shear stress, the maximum in-plane shear stress is, what the shear angles are, and then finally, what's the corresponding normal stress with that maximum shear stress? So the first thing that I'm going to do with this is, and where you should always really start with these plane stresses, is just write out what you know because signs are important. So my x is 50 megapascal. Now my y, important thing to make sure here, it's in compression, so that's negative 10 megapascal. And then tau xy. Now, positive and negative on this one. This is a positive 40 megapascal. How do I know? And it's basically the easiest way to remember would be they're kind of when these guys are both pointing to the positive coordinates. Because if you think about this as just a regular coordinate system in your quadrants, I believe the quadrants are 1, 2, 3, and 4. This would be the positive one because I've got a positive number this way, positive number this way. I multiply the two of them together, I'd have positive. This would also be a positive because this would be the negative x, the negative y. Two negatives together would be a positive. And then you have one negative, one positive here, one negative, one positive here. So, or you can remember it's always to the upper left, or it's always stretching the element that way. Whatever it takes to remember that. But this would be the positive direction. So the first thing to do is we calculate out, okay, well, got an equation, tangent to theta principal is equal to 2 tau xy over stress of x, stress of y. And so all this is going to be 2 times 40 megapascal. I'm going to be leaving the units out of this just because they're all megapascal and I know the units are going to cancel, so I'm not so much worried about it. So 50 megapascal minus negative 10 megapascal, and that's going to give me 1.333. Now, obviously, we need to do the arctangent, and once we do the arctangent, we can get that 2 theta p. There's going to be two solutions. We've got two roots, 53.1 degrees and 233.1 degrees. And so finally, our principal angles will be 26.6 degrees and 116.6 degrees. So there's our principal angles. So we're going to rotate everything to those angles. So let's determine our principal stresses. Principal 1 and 2 are going to be stress of x, stress of y divided by 2, and then plus or minus the square root of stress of x, stress of y over 2 squared plus tau xy squared. And so once again, I'm not going to put the megapascals in because the units are all the same. They're all going to cancel out, so I'm not really worried about that. So 40 minus 10 divided by 2 plus or minus, sorry, not 40, 50. Plus or minus 50 minus 10, and that's actually plus. Got to pay attention to the mathematics when you do this one, because that's where it's really easy to screw up, as I just did twice there. And so once I do that, what do I end up with? Well, that's going to be 20 plus or minus, what is the square root of all that? I've got it written down here. So 30 squared plus 40 squared, square root of all that. And so you're going to end up with stress 1 and stress 2. You will have 70 megapascal, and then you're going to have negative 30 megapascal. But we're not quite done, because that only tells part of the story, because I don't know which one of these angles correspond with which one of these stresses. So what I do is I go back to, remember, our initial equation. So there's x prime is equal to sigma x plus sigma y over 2 plus sigma x minus sigma y divided by 2 cosine 2 theta plus tau xy sine 2 theta. So what do? I can take that number, plug it in there, and that's going to give me one of my two principal stresses. Why do I have this other equation then if I can just do that? This equation's quicker and will give you both the principal stresses right off the bat, and not all the time do you need to know which principal stress and which angle go with each other, but this is a way that you can sit there and do it. So a lot of times they'll just ask you what the principal stresses are. They won't ask you the directions. Sometimes, especially if I do it, I will. And so basically if I plug 26.6 into this equation here, that's going to give me an x prime of 69.99999, so it's basically the 70. So what you would do is say the first principal stress is 70 megapascals at 26.6 degrees, and this one would be at 116.6 degrees. And so that would be the full out, complete answer. Okay. So there's our principal stresses. That takes care of that. Nice and easy. So now let's go and take a look at our, actually here. Let's erase that. And you can see I've got that all rotated in there. So now let's go and look at calculating out our maximum in-plane shear stress. So I just these are just a copy over of the stuff from the other one. Tau max in plane is going to equal the square root sigma x or sigma y divided by 2. Square that difference plus tau xy squared. And so now if I plug in all those numbers, we're going to end up with 30 squared plus 40 squared. Take the square root of the whole thing. And so the maximum in-plane shear, once we solve that, is going to be 50 megapascal. Now, once again, want to figure out what the maximum in-plane shear stress is. We can go back to our equation, but there's one little trick that we've got from everything that if you think back to when we were doing our entire concept of doing the normal and the shear stress, and we've seen this a couple times, we should remember that our maximum normal stress is always going to be our maximum shear stress is always going to be 45 degrees off our normal stress. So we can use that equation, or we can also just say that my maximum in-plane shear angle is going to be the principal minus 45 degrees. And so I already calculated that stuff out from before, so if I do that, I get negative 18.4 degrees for my first principal strain, principal shear stress, and then my second one would be 71.6. So there's my shear angles. Now remember, my maximum in-plane shear stress plus minus doesn't really matter because it's always just going to be, it's going to be the same shear stress, but our angles are important to get to where we're going. Okay, and actually I think there's my picture of my rotated element showing in my principal shear angle. I know that the book has P there, that really should be S. Okay, last thing, corresponding normal shear stress. What's that going to be? That's going to be the center of my circle. So the corresponding shear stress is just going to be the average stress for the situation. So stress X plus stress Y divided by 2. 50 minus 10 divided by 2. I haven't written in the units because they're all megapascals. I know that's what it's going to be. So that stress is going to be 20 megapascals. And so that's going to be the normal stress where our shear stress is maximized. And the other interesting thing with that is that's going to be for both the X and the Y values, because that's going to be the average stress, so the transform stress is going to be the exact same. And once again, that's kind of captured in this picture. You can see the normal stress along the X transform and the Y transform are both going to be 20 megapascals.